Hello. So, spontaneity. We've been talking about spontaneous reactions before with entropy, delta G. Now let's do our E naught of our cell. So, a spontaneous reaction will take place if the reduction half reaction is on top of, in the table, is higher up than the oxidation half reaction. If it's the other way around, then the reverse reaction would be spontaneous. So let's look down here at these two reactions, right? These are both reduction reactions. You can see that the E naught of the copper 2 plus has a higher reduction potential. That means that the copper 2 plus prefers to be reduced and that the zinc would prefer to be oxidized. That means that when we look up here at our reactions, we said that the copper prefers to be reduced, and this is the reduction reaction. So the copper 2 plus prefers to be a reactant because the reduction potential value is greater than the reduction potential value of the zinc. So if it is paired this way, it is going to be a spontaneous reaction. The E naught of the cell would be positive, so it would be spontaneous. Thus, the delta G would be negative, right? Because it's the opposite. We know that negative is spontaneous. And that means if we pair it the other way, if now our copper, instead of being reduced, is being oxidized, that's not as favorable. That is not going to be a spontaneous reaction. And so our E naught of our cell would be negative and it would be non-spontaneous. Thus, our delta G would end up being, that should say, positive. So without calculating E naught of our cell, can we predict if this reaction is spontaneous? And if it is, sketch the cell. Well, let's see. What's happening? So our zinc solid, right, is going to zinc 2 plus. So that means what's happening? Is it being oxidized or is it being reduced? Well, it looks like to me it is going from a 0 to a plus 2. That would be a loss of 2 electrons. So this would be an oxidation reaction. Our iron is being oxidized to iron 2 plus. That means our magnesium is going from plus 2 to 0. It is gaining 2 electrons, so it is being reduced. So what we want to see when we look at the table, we want to see that the magnesium reduction reaction is higher on the table than the iron reaction. So let's look at our table. So here we go. They gave us some values. So on our table, we said that we wanted our magnesium reaction to be higher on our table. Well, it was a negative 2.37 volts, whereas the iron was a negative 0.45 volts. So this one is more negative. We wanted the more negative one to be the oxidation reaction. So therefore, this reaction is not spontaneous. We would want the more positive one to be the reduction. And the more positive one here ends up being our iron. So that means if going this direction is not spontaneous, how could we make it spontaneous? Well, we could flip it around, right? We could write our iron is going from iron 2 plus to 0. So it ends up gaining 2 electrons. So it is the one that is reduced. And now our magnesium is the one that is oxidized. This would be a spontaneous reaction. We can then draw this. We know that, let's see, we said the iron is being reduced here, right? It's going from iron 2 plus, gaining 2 electrons to iron 0. Reduction happens at the cathode. So over here at my cathode, right, I always draw the anode and then the cathode. So at my cathode, I'm going to have my iron solid is my electrode, and I'm going to have my iron in solution. At the anode, I'm going to have my magnesium solid in a magnesium solution. These ones are both 1 molar solutions. You need to make sure you have a closed circuit, right? So here's our closed circuit. We have our flow of electrons going to the right, and we also have our salt bridge. Remember, our cations and our salt bridge would be attracted to our cathode. So technically, if we had some salt in here, let's say KCl, right? Potassium would be our positive cation, so that would be attracted to our cathode. Our anions would be attracted to our anode, so that would be the chloride ions. So what about metals? We've done metals before. We have dissolved metals in acid. So most metals will dissolve in most acids, but some will not. How do we figure out if it is going to dissolve or not? So if the reduction of H plus is easier than the reduction of the metal, then the metal will dissolve. So what that means is the ion reduction potential reaction has to lie below the hydrogen plus reaction. So if we take a look, so H plus is at 0 volts, right? Here's the H plus reaction, because H plus would be our hydrogen ions. So it'd be hydrochloric acid, hydrofluoric acid, hydrobromate, right? Any of our acids that have hydrogens. So it wants to reduce from H plus to H2 gas. It will only dissolve it if it is below this. So iron 3 plus or iron solid would convert to iron 3 plus. So it would dissolve. Let's see, lead would dissolve, tin, nickel, cadmium. All of these metals here would dissolve in acid. If we look up here though, which ones? Let's see, copper. Copper solid. Copper does not dissolve in acid. Same thing with, what else do we have up here? Silver. Silver does not dissolve in acid. Interesting. But what we could look at is nitric acid. So nitric acid does have the same reduction reaction, right, of the hydrogen ions, but it also has another reaction. It also has the NO3 reaction plus the 4 hydrogens. So it has a higher reduction potential. So now, if we're looking at anything below nitric acid, look, silver is below nitric acid. Same thing with platinum. Platinum is below nitric acid. So we can actually dissolve more metals in nitric acid because it has a higher reduction potential. So it's interesting though, right, that some metals, so silver, will only dissolve in nitric acid, but we could take copper and we could dissolve it in nitric acid or hydrochloric acid or hydrofluoric, hydrobromic. Any of those acids will work, but the only one that will dissolve silver is nitric acid. So how do all of these reactions go together? They actually do all correlate. If we take a look, so first, a spontaneous reaction. For a spontaneous reaction that proceeds in the forward direction, we need to have a delta G less than 1, right? It needs to be negative. An E naught has to be greater than 1. It has to be positive. And our K has to be greater than 1 in order for it to proceed in the positive reaction. So we have this correlation between our different values. So if I was given E naught of a cell, I could solve, right, my delta G. If I knew delta G, then I could solve my K, because I could plug it in here and solve what my equilibrium constant was. I guess I could have just gone straight there if I had E naught of our cell, right? We could have solved for K. So these are all interrelated to each other if you need to use one thing versus another. So our delta G equation, we had negative RT ln of K last chapter, but now we're adding a new one. So now we have negative NF E naught of our cell. So N is the number of moles of electrons that we have, right? Each reaction has some number of electrons. And F is Faraday's constant. So Faraday's constant is down here, 96,485 coulombs per mole of electrons. And we can solve delta G. So use the tabulated electrode potentials to solve delta G. Is this reaction spontaneous? Well, first, what do we need to do? Well, let's take a look back. Delta G, how can we solve it? Well, we can solve delta G equals negative NF E naught of our cell, or delta G equals negative RT ln of K. Well, we don't have K, right? So we can't do that one. And then we also don't have a temperature. But we could use the electrode potentials, right? Use Faraday's constant, use the number of moles to figure out our delta G value. So what we need to do is we need to figure out what is E naught of our anode and what is E naught of our cathode from our electrode potential chart, so we can figure out E naught of our cell. Then we can use E naught of our cell, right, and plug it in our delta G equation. So if we separate our two half reactions, we would have to figure out which one's being oxidized and which one's being reduced. So let's go back for a second. Our iodine is going from solid, right? So its oxidation number is 0 to a -1. So it has gained, right, 1 electron. If it gains an electron, that is being reduced. So that means our iodine's being reduced and our bromine's being oxidized. So let's see. Bromine is being oxidized. Iodine is being reduced. Okay. We found our values in our table, so you just need to look them up. E naught of our cell is our cathode minus our anode. So 0.54 minus 1.09, we get a negative E naught of our cell. Automatically, we know that a negative E naught of our cell means that it's not spontaneous. So that means when we solve delta G, we know right off the bat delta G has to be positive, because a positive delta G means it's not spontaneous. Okay, when they balance those reactions, right, you need to end up having 2 electrons. That would be N, that would be your moles of electrons. So delta G equals negative N, so that would be 2 moles of electrons, F, which is Faraday's constant, times negative 0.55. Another unit of volts is joules per coulomb. So our coulombs cancel, our moles of electrons cancel, we end up having a delta G value that is in joules. We got 1.1 times 10 to the 5th joules. That makes sense that it's positive. We said positive is non-spontaneous. This delta, or this E naught of our cell was negative, which means it's non-spontaneous. So overall, we were able to calculate our delta G. So please try this one, pause this video, do the same thing, double check your answer, and then see me back for our next video.